In this short video, we're going to learn how to find the cost minimizing choices of labor and capital when a corner point solution appears. So let's imagine that SledWorks, a company that produces sleds, has the production function 20 k to the 0.5 plus L, where L is hours of labor hired and K is hours of capital hired. The firm wants to produce 100 sleds. The wage is $20 an hour and the price of capital is $10 per unit. Our goal is to figure out how many units of labor and capital the firm should hire in order to minimize their costs. What do we need to know in order to solve this question? We need to have a production function, an output goal, as well as prices for both of the inputs. How are we going to solve this question? Well, we're going to start out by applying the tangency condition, which tells us that the slope of the isoquant has to be equal to the slope of the isocost line, as well as the isoquant condition, which tells us that production has to equal 100. However, in this question, we really want to understand what happens if things go wrong. And in particular, what happens if, as we're solving this problem, we reveal an optimal value that's negative? Well, if we find that L is negative, then we know that L should be equal to 0 and K should be hired. Capital should be hired until 100 units are produced because that's how many sleds this firm wants to produce. If instead we find that capital is negative, then we know that L, or labor, has to be hired until 100 units are produced, and that K is equal to 0. So the negative value is going to tell us which input is not hired, and then we'll just use our isoquant condition, or our production constraint, to figure out how much of the other input has to be hired. Let's see how we solve this question. So here's what we know. We have a production function, a wage, a rent, and an output goal of 100 sleds. And we are looking to find the cost minimizing choice of labor and capital. So in this question, we're going to sort of proceed as if we do not know that a corner point solution is going to appear. So we'll follow the established protocol. We'll compute the marginal products, then the tangency condition, and we'll write down that isoquant condition. So starting with the marginal products, we know that the marginal product of labor is the partial derivative of the production function with respect to L, and that's going to be equal to 1. The marginal product of capital is the partial derivative with respect to K. So I'm going to bring down the 0.5, and it's going to multiply by the 20 to become 10. And then I have K to the 0.5 minus 1, which is minus 0.5. Using these marginal products, we can compute the tangency condition. We need the marginal product of labor, which is 1, divided by the marginal product of capital, 10 k to the negative 0.5, to equal the wage over the rent, where wage is 20 and rent is 10. I'll call this equation 1. So this is guaranteeing that the slope of our isoquant is equal to the slope of the isocost lines. Now we also need to be sure that we achieve our production goal. So we're going to write down the isoquant condition, or you can also call this the production constraint. This is just a matter of making sure that our production, 20 k to the 0.5 plus L, is equal to the required 100 sleds. We'll call that equation 2. Using these two equations, we're going to solve 1 for K. Now, K is actually going to give us solving 1 for K is going to be a numerical answer. And the reason why this is a bit simple is because this is a quasi-linear production function where the marginal product of labor is 1. So I need to start shuffling things around. In my equation 1 here, I have a negative power in the denominator, so I'm going to move that up. And at the same time, I'm going to simplify 20 over 10 to be equal to 2. So I'm going to rewrite this as k to the 0.5 divided by 10 is equal to 2. Then I'm going to multiply both sides by 10. So I have k to the 0.5 is equal to 20. Finally, I want to isolate k, so I'm going to square both sides of my equation. And I end up with k is equal to 20 squared, which is 400. Now I'm going to take what I learned on the previous slide, that k is equal to 400, and I'm going to substitute that value into my isoquant condition to find L. So I have 20 times 400 to the 0.5 power plus L is equal to 100. Well, 400 to the 0.5 is 20. So I have 20 times 20 is equal, plus L is equal to 100. Well, 20 times 20 is 400 plus L is equal to 100. I hope you can see that things are going to go horribly wrong in my next math step. If I subtract 400 from both sides, I get that L is equal to 100 minus 400, which is negative 300. That's clearly not possible. You cannot hire a negative amount of labor. So what are we going to do? We're going to talk about this for a minute. Our tangency condition and isoquant condition have kind of like let us down in a sense. We've solved for the point at which the slope of the isoquant equals the slope of the isocost line, and at the same time we're on the 100 unit isoquant, and we found that it occurs in the wrong quadrant, right? We're hiring 400 units of capital and negative 300 units of labor. This doesn't make any sense, so we have to completely reevaluate what's going on. When I say reevaluate, I mean the first conclusion we're going to draw is that L is actually equal to 0. A really common student error at this point in the question is to say that the solution is L equals 0, K equals 400. That is simply not true, and you can confirm that if K is equal to 400, then the quantity we produce would be astronomically high, way more than 100 sleds, so that can't possibly be the cost minimizing choice. How am I doing that? I'm looking at the production function, and in my head I'm doing 20 times the square root of 400. Square root of 400 is 20. So 20 times 20 is 400 plus 0. That's 400 sleds, and I only need 100. So this cannot be a solution. L equals 0 and K equals 400 is not a solution. We're completely reevaluating. We know L is 0 because we solved that it was negative 300. Now what do? We go back to the isoquant condition. This has to hold. We must produce 100 units. We plug in what we know, that L is 0, and we can solve for K. So we have 20, K to the 0.5 plus 0 equals 100. That means K to the 0.5 is equal to 100 divided by 20, which is 5. We square both sides, and we get that K is equal to 25. Now, check to make sure your math works. Take the K back to the production function. 20 times the square root of 25, well, that's 20 times 5. 20 times 5 is 100. So we've met our goal. It's always good to check, especially when you have this corner point solution up here. It's always good to check at the end that it all works out. So we've solved this problem. We ran into a roadblock. We got a negative number. We reevaluated, and we figured out that the cost minimizing choice is 0 units of labor and 25 units of capital.